does dictionary work in C#? A dictionary is one of the most common and useful structures. It is able to store and get values with a unique key. At the same time, to do it as efficiently as it possible. Averagely, the complexity of all the operations are all from 1. In this video, let's look into the details of how it works in C#. The basic knowledge that we need is that insert, search, delete operations in an ordinary array by index take O from 1, because in this case we get a specific area of memory. Basically, that's how it works, and everything that we need is with a key of any type to define the index of the element in the array. Any object in C# has a getHashCode method that returns the result of the hash function as a number. This method can be overridden, but its sense is to return different hashes for different objects. On the other hand, similar objects should have the same hash. For number 1, the function will return as 1. For the number 100, the function will return 100. For a string bar, the function will return this value for us. During initializing a dictionary inside, it has two main arrays where our data resides. The first array of integers is called buckets, and the second array of entries is an array that already contains our data. An entry is a structure that contains our key, value, hash code, and next value. The next value is used to resolve collusions. This process is called chaining, and we will consider its essence later. The size of our buckets and entries array is the same and is presented by the prime numbers from 3. If we collect more elements than these, arrays increase by 2 times as they are filled and the nearest prime number are taken. We produce the initial size of the arrays through the constructor if we understand how much data we are going to have. If you want to see adding values with a key and value as to string, then it looks like this. We create our dictionary. Since our key is a string, especially for string type, we have a special compiler working to generate a non-randomized hash for strings for better performance. However, if we have reached an increased threshold for the number of collusion equal 100, then the compiler is replaced with the default one for string, and all hashes are recalculated. Initially, buckets and entries are two private fields, and both of them are null. Let's add a couple of foo1 bar1. We initialize our arrays, buckets and entries, and the first prime number is 3. The size is important to us, and here is why. We call the function getHashCode for foo1, which is this number, but we can't enter value at this index because we only have 3 places in the arrays. Now we take a remainder of division this number by 3 and take 0. Now we find where we can put our key value, and the first free place in the entries, it is a place with index 0. We write our entry there. Now in the buckets at index 0, which has been obtained from the remainder of the division, we will write the index of our entry in the entries like O plus 1, because the buckets is filled by zeros by default anyway. Do the same with the pair foo2 bar 2. A remainder of division this number by 3 is 1. The next free place in the entries at index 1. Let's write our entry there. Write 2 at index 1 in buckets. Now let's add a pair of foo3 bar 3. This hash, a remainder of division by 3, is 1, and this is very collusion, because at index 1 in buckets we already got an index on foo2. We would like to put foo3 in the next available place, but we can't because the algorithm doesn't work like that. We put foo3 in the first place of 3 entries, it is an index 2. We add 1 to the index 2 and write the 3 in the index 1 in the buckets. But in order not to lose foo2, we write the foo2 index in the field next in foo3. In our case, it is 1. How do we get foo2 now? We calculate the hash code from foo2. It hasn't changed. It as before, it is this number. The division from it by 3 is 1. Now we go to the buckets at index 1. We find index 3 in it. Let's subtract from the index 3 1, so it is 2. We get the entry at index 2 from the entries, but this is not foo2, this is foo3 because we had a collusion. We take the next value, this is 1, and look at what we have in the entries at index 1. It is our desired foo2, we can return it. Let's now add the value of foo4. We already assume that there will be no place for it and we will have to increase. Let's see how it looks like. We, as usual, calculate the hash code from this number. A remainder of division by 3 is 2. Let's go further and catch that we don't have a place to put foo4 in the entries. Let's go to expand arrays, entries and buckets. The current value 3 is multiplied by 2, it will be 6. We take the nearest prime number 7. Create new arrays of entries and buckets of size 7. Entries are copied as is from old to new one. Now iterate over all entries. They already have a hash code and we don't need to recalculate it, but we need to recalculate the new place with the new length of array. We iterate over each one and write its index into a new place in buckets.